Good day. For those of you who do not know us, we're the instructional staff for ECE 150, Professors Hiran Patel and Werner Dietl, and Douglas Harder. In this topic, we are going to discuss issues with member variables. So in this topic, we will observe there are some issues with our classes. We will see that any fixes we implement can nevertheless be subsequently corrupted by the user. We will introduce the idea of encapsulation, that is, protecting the data in an object from the user, either deliberately or accidentally changing the values. We will see that the critical times in an object's life are how the object is initialized when it is created, that is, declared or instantiated, how the user accesses and manipulates the object during its lifetime, and how the object is cleaned up when it is destroyed, that is, when it goes out of scope or is deleted. Now, we've already introduced a rational number class, but what happens here? If we initialize the rational local variable p with the default values, we get the ratio 0 divided by 0, but this is not a valid rational number. However, there's nothing that we can do to prevent a user from using our class like this. Also, a user may either incorrectly, through not understanding a rational number, or accidentally set the denominator equal to 0. Under these circumstances, none of the subsequent arithmetic operations are defined correctly because anything over 0 is not a rational number. One solution is to begin every function and operator with a check to ensure that any denominators are not 0. This is going to be expensive, however, as this check is a good percentage of the runtime of this particular operator. That's going to slow the system down, and on top of that, it's going to punish those users who are indeed using the rational number class correctly. However, the problem is, as long as the users have access to the member variables, we are more or less forced to make such checks. Now, here's another issue with our rational number class. The user could initialize any of these local variables to be a rational number, and yet they are all the same. All of these represent the rational number -1/2. Wouldn't it be great if all of these were stored the same way? So to ensure that all of these are stored the same way, we could require that the denominator is a positive number. So if it is a negative rational numbers, it is the numerator that is negative. If it is a positive rational number, both the numerator and denominator must be positive. Also, we should ensure that the greatest common divisor of the numerator and denominator is 1. These two rules make the representation unique. Now, we call this in computer engineering a normal form. However, you will cover this more in your third year courses. However, what's important here, if two rational numbers are in normal form, then both the numerator and denominator are equal. Now, for example, to ensure that this is true, we could do the following. When we add two rational numbers, we can calculate the numerator and denominator. We can then calculate the GCD of the numerator and denominator we just calculated. Now, this of course requires us to author a GCD function, and we should assume that it returns a positive integer. Just in case, we check the denominator. If the denominator is negative, we will negate both the numerator and denominator. That is, we'll multiply both the numerator and denominator by -1. Finally, when we return the constructed new rational number, we will divide both the numerator and the denominator by the divisor we found. Problem, however, if we were guaranteed that all rational numbers were in this normal form, then we could actually compare two rational numbers simply by comparing their numerators and their denominators. And as you can imagine, this is a very fast check in hardware on the computer. Unfortunately, this is not the case, because while we can ensure that all our functions return rational numbers that are in normal form, the user may nevertheless initialize a rational number so that it is not in normal form, and the user may accidentally or intentionally assign a numerator or denominator so that the resulting rational number is no longer in normal form. So we are stuck with performing two multiplications, which, as you can imagine, is much more expensive than a comparison, and then we have to compare the result of those two multiplications. Now, one interesting point is we could ensure normalization in our functions rather than doing it separately every time by authoring the following function that takes a rational number, checks that it's in appropriate form, that the denominator is not zero, and then converts it into a normal form. Now, if we use this function, this would also, of course, we could now calculate the sum of two rational numbers as follows. We could normalize both p and q, calculate the result, normalize the result, and then return it. Now, there are some problems here. We can no longer declare p or q to be constant. So now, if we calculate the sum of two rational numbers, we may actually change the arguments. Is that a good idea? Probably not. Also, there's a lot of overhead going on here. We're calculating the GCD 3 times, and if P and Q are already in normal form, the GCD of P and Q initially will be 1, so we've done a lot of work for no benefit. Also, we could write the equals operator by first normalizing them and then simply comparing if the numerator and denominator are equal. But once again, this requires us to calculate two GCDs. And if the user was ensuring that numbers or rational numbers were always in normal form and not accidentally initializing a rational number with a non-normal form, we're still doing a lot of extra unnecessary work. Again, we can't declare P or Q to be constant because we may actually normalize P and Q. So we have to change them. So once again, this is undesirable. Now, a serious issue here is more work is now being done checking and normalizing the numerator and denominator than the actual operations that are being performed. The problem is we can never assume that rational numbers are normalized because users may accidentally or unintentionally change any member variable of any instance of a rational number. Now, if you are writing this class for yourself, no problem. You know exactly what you're doing because you wrote the class. But you're going to be an engineer. And in industry, your class is not only going to be used by you, it will be used by other employees or other groups within your company. It may be used by your clients or your customers or the public in general. And most importantly, it's going to be used by whoever replaces you in your position when you either leave or are promoted. And they may not know all the subtle details of your class. They're not going to have time to investigate, read all your documentation before they start using that class. Next, let's discuss our array class. Here are all the problems with this class that may occur. Actually, not all problems, but a significant number of them. First of all, a user may not even initialize an instance of the array class. So data may just be declared to be an instance of the array class, and immediately you have a wild pointer because the member variable array is not initialized. It may be initialized with default value, in which case the array is now a null pointer. The user may accidentally assign to the array member variable some other value, perhaps a null pointer or another newly allocated array, in which case you end up with a memory leak. And the user may have forgotten to call an appropriate cleanup function. And if that's the case, this too results in a memory leak. Additionally, the user may simply assign the wrong capacity. So the array may be initialized to be a dynamically allocated array of capacity 500. However, if capacity is assigned to 100, subsequent algorithms may assume there are only 100 entries. On the other hand, if only 500 entries were allocated, but the user accidentally assigns capacity to be 1,000, now subsequent algorithms are going to assume that additional memory has been allocated even if it was not. Now, all of these problems exist because the user is not required to follow any sequence of statements to initialize an instance of a class. At any time, the user can change any member variable of an instance to whatever they want, even if that change is accidental. And an object assigned to a local variable may go out of scope, or the user may call delete on a dynamically allocated object without properly cleaning up any additional memory. Now, in the old days, C libraries offered no additional protections because C does not have additional protections that C++ has. And many commercially available libraries simply assumed you were not making any mistakes. The assumption is that the programmer was experienced or a veteran programmer. This made it especially hard to find bugs, especially for new programmers. I remember the first time I was attempting to author a program that used the X Windows graphical user interface. I got it working, but there were difficulties. To fix these problems, we must deal with the lifetime of the object, from the creation of the objects, during its existence, all the way to its destruction. So these are the three separate aspects that we will look at solving. This includes correctly dealing with the initialization of an object during its creation or declaration, allowing the user to access and manipulate the object without ever having the opportunity to accidentally corrupt data or leave the object in an inconsistent or unnormalized state. And this is through not ever allowing the user to directly access or assign to member variables, ever. Finally, correctly dealing with the cleanup or destruction of an object. So, to introduce the terminology, constructors will be functions that deal with object initialization. Member functions will allow the user to access and manipulate objects, and destructors will deal with the cleanup of objects. So our classes currently have member variables. We will introduce constructors, additional member functions, and destructors for our class. Now, the process of protecting data from the user is called encapsulation. This comes from biology. A biological cell has a membrane that encapsulates the cell. All information, including mitochondria, DNA, and other proteins, are protected inside the cell by this membrane. DNA itself is actually protected inside the nucleus, which is a cell within the cell. The membrane prevents anything other than what is required to enter the cell. Well, at least it tries to prevent anything else. So the membrane blocks ions and larger molecules, for example. It does allow smaller molecules like water to penetrate. There are transport proteins on the membrane surface, however, that facilitate the transfer of specific molecules like glucose into the cell, which is then used for energy. Now, one important word of warning. Encapsulation in C++ is not security. Even if you use all the tools we will introduce, I can, with one line of code, break that encapsulation. Sort of like having a back door. Such breaking of encapsulation requires a very deliberate statement in C++ that is normally never used. So this isn't really a problem. It's something that you have to explicitly do that is useful under very, very few other circumstances. However, it's important to understand that classes protect honest users from making mistakes. They do not protect users from dishonest other users who intend to break the process. So, following this topic, you now are aware that there are issues with users being able to access and manipulate member variables. You understand to fix this problem, we cannot allow the user to access member variables. You know there are three aspects of an object's lifetime that we must secure for the user. That is, the object's creation, the accessing and manipulation of objects by users, and the object's destruction. You are aware that this will be performed through encapsulation with constructors, member functions, and destructors, respectively.
Here are the references,
Acknowledgements,
the colophon, and a disclaimer. Cheers!